guys, so first of all, I apologize for the really small font, having some technology issues, and this is the only way I can get it to work right now. So this is going to be the beginning of continue to talk about heat. We've been talking about heat transfer and how heat transfers, but this is going to take into account sort of a larger area of study that happens. And a lot of things we've already talked about, like calorimetry and whatnot, does fit under this title of thermodynamics. You can see up at the top, and you can define on your paper, that thermodynamics is the study of heat and heat transfer. It's not only physical changes, though. We've only been talking about physical changes and how heat transfers in a physical manner, like when we heat a piece of metal up and put it in cool water, or what's happening when a liquid becomes a solid or a solid becomes a gas, etc. Now we're going to talk about chemical reactions. So you see down here in your examples that you are looking at chemical reactions now. So it's not any more difficult. It's really just stoichiometry, which you already know how to do. Let's start by defining a couple more things that you do already know. We've learned before, but we'll redefine them. The terms endothermic and exothermic are really important in this chapter. So if you remember, exothermic means releases heat. So if you have an exothermic reaction, you're releasing heat. And endothermic means absorbing heat. Okay, and again, those are really important concepts. Now, what we're going to learn today that's new is this thing delta H. Okay, that's called the enthalpy change. Enthalpy is a word that essentially means heat. Okay, so if you see the word enthalpy, you're to think really it's a heat change, and you can see that's why it's a capital H. Please don't think that delta H is temperature. Remember, temperature is a measure of average kinetic energy. This is heat content. So that those two things are different. Heat content takes into account other things that temperature does not. So enthalpy change is defined as the heat absorbed or released during a chemical reaction. And again, there's the difference between what we've done before and what we're doing now. Now we're talking chemical reactions. If you calculate the enthalpy change, which is what we're going to learn how to do, if the reaction's exothermic, then the delta H is negative. So a negative delta H means the change in heat. Remember, delta means change. So the change in heat is being released. It's being given off. Endothermics are always positive, delta H's. You need to learn those two signs and what they mean. So if I say what is exothermic delta H's, you should be able to immediately tell me that that is negative. Now the calculations for these, again, are pretty simple because they are stoichiometry problems, and you know how to do stoichiometry problems. We're just going to add a new conversion factor, so it shouldn't be too bad. Let's jot down these steps, and then I'll show you with a problem. So it says convert from grams to moles, and you can see in parentheses it says using molar mass, which you know how to do. Then it says convert moles to, and then this should be kilojoules, using the delta H relationship established in the equation. So take a look at the first example problem. I'm going to show you how this works. First, look at the reaction and look at the delta H. Okay, they are tied to each other. They're married to each other. What this reaction is telling you is that for every two H2O2s, you're going to make two H2Os and one O2. And at that time, you're also going to make 190 kilojoules of energy. The reason why I said you're going to make it, release it, is because it's negative. You see that negative on there, and remember that means exothermic reaction. So this reaction is going to make 2 moles of water and 1 mole of O2, and also is going to make 190 kilojoules of energy. That is a set fact. So for every 2 moles of H2O2, you get 2 moles of H2O and 1 mole of O2. Now they come along and tell us we don't have 2 moles of H2O2. We only have 1 gram of H2O2. So we know the relationship, just like when you're converting from, say, inches to feet. There's 12 inches in a foot, but I don't have to always say I only have 1 foot. If I told you I had 4.5 feet, you can still figure it out using that relationship. So here's how the problems work. Remember, step 1 is convert from grams to moles. So 1.0 grams H2O2. Set up a stoichiometry. So for every 1 mole of H2O2, you're going to have 34.0 grams. That's just its molar mass. Okay, that gets rid of the unit of grams. Then we're going to do another conversion factor. This one, we need to get rid of moles of H2O2, and we need to convert into kilojoules. Okay, and again, that relationship is up here. We're using H2O2, so I'm going to only look right here. I'm going to see what the coefficient is on that H2O2, and that goes on the bottom of the mole to kilojoule step. Notice I'm still using 1 mole over here for my mole conversion, because that's always 1 mole. But in this step over here, this mole to kilojoule step, I'm going to use the coefficient. And then the number that goes with kilojoules is this number. So negative 190. If this problem had been about O2, see, I would have put 1 down there because there's a coefficient of a 1 with O2. But it was about H2O2, so I put the right coefficient. Okay, and then we're just going to do our stoichiometry math. I'll help you with this. Oopsie daisies. So when you plug that in, you get negative 2.8 kilojoules. Okay. So that's how much energy would be given off by 1 gram, which makes a lot of sense. If 2 moles gives off 190 kilojoules, 1 gram is way less than 1 mole. So it's going to give off a lot less energy. So it's all just proportional. Okay. Now in this next one, we have 9.22 grams of C2H12O6. But again, here's the relationship, the standing relationship. Doesn't matter what we start with. We know that 1 mole plus 6 moles makes 6 moles and 6 moles and makes this much energy. So we have the relationship we need. So we're going to start with 9.22 grams. I do not know what's going wrong with my pen all of a sudden. C6H12O6. I wonder why it's doing that. All right. Hopefully it won't be too messy. And then you're going to put grams of C6H12O6 on the bottom and convert into moles. Okay. For every 1 mole, remember this is molar mass, and the molar mass, by the way, of that is 180.0. Oh my gosh, it looks so bad. So sorry, guys. I don't know why my pen's like dragging on the computer now, but anyway, so this is grams canceling out, okay, and then we're going to be putting moles of C6H12O6 on bottom, and then on the top we're going to be putting kilojoules. And again, the way you convert from kilojoules to moles, the kilojoule value is always this number. That's easy, so we'll put negative 2803. And then the mole value comes from the coefficient on that substance. So for this one, the coefficient is a 1. So for this problem, it does end up being 1, but it's not always. It has to be the coefficient. Multiply that out, and we're going to get negative 144 kilojoules of energy. So it's just a new type of stoichiometry problem, one that you already know how to do stoichiometry. So it's just a matter of applying a new conversion factor. So again, find the substance in the problem, that's the coefficient, and then the delta H. That's how you're going to get this new conversion factor that we used right here and right here. All right, so you have some homework problems to try on these, and if you go through and do them, you'll see on your worksheet it's sort of cut in half. I did the problems over on the left side, and then there's a lot of space on the right, so you can just do your work right next to that. And if you have any struggles, just make sure that you definitely are doing some work. I mean, you can see this is the same format for every single problem. So even if it's you have a question and you still need to clarify something, there isn't a reason why you shouldn't have work for every single problem.